Hi everyone, myself Professor Sridevi. In this video lecture, we are going to learn about stability analysis using RouthHurwitz criterion. The RouthHurwitz stability criterion is having one necessary condition and one sufficient condition for stability. If any control system doesn't satisfy the necessary condition, then we can say that the control system is unstable. But if the control system satisfies the necessary condition, then it may or may not be stable. So the sufficient condition is helpful for knowing whether the system is stable or not. Definition of stability. The term stability refers to the stable working condition of a control system. Every working system is designed to be stable. In a stable, response or output is predictable, finite and stable for a given input. That is, the different definitions of stability are: the system is stable if its output is bounded for any bounded input. A system is asymptotically stable if the absence of input, the output tends towards zero irrespective of initial conditions. These all are the definitions of stability. RH criterion is one of the criterion which is used to define the stability. The necessity condition is that the coefficients of the characteristic polynomial should be positive. This implies that all the roots of the characteristic equation should have negative real parts. So the necessary condition is that the coefficient of the characteristic polynomial should be positive. This implies that all the roots of the characteristic equation should have negative real parts. That is, considering one characteristic equation a0 s power n plus a1 s power n minus 1 plus etc. up to an s power 0 is equal to 0. Here the missing term nth order characteristic equation. This means the nth order characteristic equation should not have any coefficient that is 0. And we have to consider in RH method, the roots of the characteristic equation exist to the left half of the S-plane, then the control system is stable. If at least one of the root of the characteristic equation exists to the right half of the S-plane, then the control system is unstable. So from this we have to find the roots of the characteristic equation to know whether the control system is stable or unstable. But it is difficult to find the roots of the characteristic equation as order increases. So for increasing order, we are moving for RH criteria. In this RH criteria, we are going to write down RH array with the coefficients of the polynomial, with the powers of the polynomial s power n, s power n minus 1, s power n minus 2, s power n minus 3, etc. up to s naught. Here a0, a2, a4, a6 are the even coefficients, and a1, a3, a5, a7 are the odd coefficients. b1 is calculated as a0, a3 minus a1, a2 divided by b1. Similarly, c1, c2, b1, b3, all the coefficients are calculated with this condition. So after calculating this, we can identify the sign changes. If two sign changes in this column, in this first column of RH table, here the control system is unstable. In the RH stability system, we can know whether the closed loop poles in this left half of the S-plane or on the right half of the S-plane or the imaginary axis. So we find that the nature of the control system to overcome this limitation. This to overcome the limitations of the RH, we are moving the next technique, which is called as root locus. So from the right half of the S-plane and left half of the S-plane, we can tell the system is stable or unstable. So next, the updated version of this one is root locus technique. So by using root array, we can able to fix this system is stable or unstable. Hope you understand this session. Thank you.